Hi everyone, welcome on this video. Today's topic is about geodesics. So what is a geodesic? We will see the global definition. There exists also a local definition, but the video will be too long, so probably I will record a second video to talk about the local definition. Today we will see what is a geodesic and what is the global definition of a geodesic. Before the video start, I highly encourage you to set the playback speed to 1.25 if you want a little more fluidity. Okay, here we go. Let me share a whiteboard. All right. Great. So let's go. What is a geodesic? Today's topic. Okay, so the global definition of a geodesic, it's a word line with extremal proper time. Okay, so a geodesic is a word line with extremal proper time. All right, so maybe let me first explain what is a word line. So if you consider a space-time diagram, which is a diagram is time and space, so x, y, z, a word line is any line on this diagram, but every object in the universe are confined within the line cone, so the word lines are always time-like, which is to say that, well, that's an example of not one, but yeah, that could be a word line. It's the line through space-time that we draw. And on this line are little scales that we call proper time. And so a geodesic is a word line with extremal proper time. Okay, so maybe we'll start with an example and yes, let's start with an example. So free falling trajectories, free falling trajectories. It's an example of geodesics. So free falling trajectories are the trajectories followed by any object that will be in free fall. So for example, the ISS around Earth, so that is Earth, and the ISS around Earth is following a geodesic. It's constantly falling toward Earth, but never reaching it. So yeah, that's an orbit. So it's orbiting around the Earth, and orbits are a kind of free fall, a type of free fall. An apple falling from a tree, that's also a free fall. And these trajectories, they extremas proper time. In so I've been talking about space-time, and One space-time that we can think about is the flat space-time. So in flat, which is to say Minkowski, the flat space-time is Minkowski space-time. So I just say in flat. In flat Minkowski space-time, the geometry is given by the Minkowski metric. So the geometry is encoded in eta, alpha, beta, which is minus 1, 1, 1, 1. So those are diagonals. And this is the flat metric or Minkowski metric. And so from this metric, we can write our line element. So we know everything about the geometry of our universe. So now I can properly draw a space-time diagram. And for example, in flat space-time, an extreme path would be a straight line. And this is the longest path possible. If we forget time for a minute, so if we forget time for a minute and consider just 3D Euclidean space, then we know that a geodesic is a straight line too. It's a straight line, but now in Euclidean space, this is the shortest. The shortest path. All right. But I'm not really explaining anything here. I'm just saying facts. So I should explain why there is all this. So let's talk about the global definition of a geodesy. The global definition is exactly what I said at the beginning, a warp line with extremal proper time. So there's the notion of extremum. So how do we find extreme path? Well, I introduced here space-time metric, for example, the Minkowski metric, and the line element. The line element at ds square, and we know the relation ds square equal minus d tau square. That's the relation between proper distance and proper time. So when we talk about proper distance, we could also talk about proper time. It's totally equivalent. And if we have a line element, then we can draw any line we want in space-time, which means that we can also draw geodesics. We can draw the extreme path, is this little line element here. This is because we know that we can write S as the integral of all um, the line element, the infinitesimal, yeah, line element. Um, ds is gonna depend on your parameter t, x, y, z, or if you're in polar coordinate, for example, it will depend on t or theta and phi. You can always choose those parameters to be function of another parameter which I will call sigma. And so you can, if you look through textbook, you can write it as such. Okay, so we can write our path through space-time like this. So far, not much new. We can extremize this path uh, from Hamilton's um, sorry, Hamilton's variational principle, which states that uh, S is an extreme path if a very small, so an infinitesimal variation of the path equals 0. Uh, that is the condition for extreme path. That is our condition. And it comes from Hamilton's principle, which is a variational principle. Right, so writing this delta S equals 0, we can also write delta S, okay, so we'll take time. Delta S equal delta, now it's gone, okay, delta L d sigma. And now analytical mechanics show that this condition here, which I just rewrite like this, is fulfilled uh, by Lagrange equations, which are the following. The strict derivative with respect to sigma of the partial derivative of your Lagrangian, this is your Lagrangian, dl dq dot minus del L del Q equal 0. And here I could have say that L is a function of the generalized coordinates Q, Q dot, and sigma. That's the Lagrangian of your system, which basically you obtain from your line elements. That's how I did it. I didn't do any magic tricks. I just got it. Here we see that ds equal L d sigma. That's how I obtain it. Okay. So this Lagrange equation, you're gonna get 4 of them because you have t, x, y, z, 4 coordinates, which means 4 equations. And if you work out a bit of algebra from these 4 equations, you obtain the geodesic equations. So you obtain 4 geodesic equations, which you can write as t square x mu ds square plus Christoffel symbol mu alpha beta, alpha beta dx alpha ds dx beta ds equal 0. Yeah. So you obtain 4 equations like this, which are the geodesic equation. You know that you obtain 4 equations like this. Also, looking at the symbols here, you have a free index mu, which will take the value t, x, y, z. So you will have an equation for xt, an equation for xx, etc. And those are the Christoffel symbols. Wait, 2f Christoffel symbols. And they tell you everything you need to know about, and I should not write this like this. They tell you everything you need to know about curvature. And you don't need to find them because if you follow this path, then they come from your Lagrangian of the system, which come from the line element. So you have everything you need to know. That, as I said, the geometry of your space-time is encoded in the line element. From this line element, you obtain the Christoffel symbols if you work out a little bit of algebra from the Lagrange equation. You can read off the Christoffel symbols, and that's the geodesic equation. I shall write global definition. And that's it. So let me summarize briefly what we done today. We asked ourselves what is a geodesics, which I answered a geodesic is a word line with extremal proper time. What is a word line? It's trajectory that we all draw through space-time, which must be encoded in your light cone. These are null word line, which means these are the trajectories of photons, which have no mass, and they go to light speed. They go at light speed, and no one can ever reach light speed. So we are confined in this light cone, and these are called word line. And word line are, because it might be interested to look at also impossible trajectories, because why not? But word line are what we call time-like trajectories. So word line are time-like trajectories. The geodesic is a word line with extremal proper time. An example of word line with extremal proper time are free-falling trajectories. This I don't know how can you see this. Free fall is a geodesic. Free fall is a geodesic. It extremely proper time. You see it in here. Also, I didn't mention, but it was relevant to talk about flat Minkowski spacetime because you know that even though you have a curve spacetime, you can always at one point approximate it with Minkowski spacetime. But yeah, With the local definition, we'll talk about curved space-time a little more. No, I don't know what to add for the free flow trajectories. I'm a little bit stuck. Free fall trajectories are geodesics because it's the natural path that the object follow in the curved space-time. And so we know that it extremizes proper time, and we see it mathematically because it fulfills what we construct mechanically here with the Hamilton's principle. Yes. So with Hamilton's principle, you can basically show that in 3D Euclidean space, straight line are the shortest path. This you can show it. And I will stop here for today. So working out the algebra from the Hamilton's variational principle, which is fulfilled by Lagrange's equation, you find the geodesic equations from which you can read off the Christoffel symbols. And the Christoffel symbols tell you everything you need to know about curvature. And this very important equation is the global definition. I mean, correspond to the global definition of what we call geodesics. It's the geodesic equation. All right. Thank you for today and see you soon.